Happy afternoon. I'm Kumar from Sri Venkatachalapati Alloys Pvt Ltd, Gumbudi. On behalf of Chennai Chapter, I'm happy to welcome you all for the technical webinar on dive deeper into your foundry defect analysis. It is handled by Mr. Veera Vignesh. He is my good friend from GC Salem. So welcome, Mr. Vignesh, Veera Vignesh.
Thank you, sir. Thank you.
Yeah. And so this is the subject is very much very interesting, and it will be very much useful for our defect analysis and to improve our performance. So we need to keep looking for the biggest, best, and the brightest in our organization. So we have to see the big picture. So that is in mind. So definitely this the webinar will help us to go into deep analysis. So nowadays the foundries are operating 5 to 10% rejection and also customer rejection. So any foundry from 5 to 15% rejection is very common. So we need deep analysis to remove the causes from our operation and to improve our performance. So I request all the participants to grab an opportunity from this technical seminar. So thank you, Mr. Veera Vignesh, and all once again, I welcome you all.
Thank you, sir. Thank you.
Thank you, sir. Sir, it's now pleasure to introduce today's webinar speaker, Mr. R. Veera Vignesh. He's a manager of applications. He's basically a metallurgical engineering graduate from Government College of Engineering, Salem. Currently, he is working as a manager of application in Snam Alloys Pvt Ltd R&D Center. His roles and responsibilities are attending to customer queries on performance and development of products, providing technical support to the marketing team, conducting customer in-product trials, coordination with quality and analytics for root cause analysis of defects occurring at customer end, development of new products to aid foundry process control improvements. His experiences 8.5 years Snam Alloys Pvt Ltd in product application. Is an exposure in mechanical testing of cast iron, metallurgical analysis of cast iron, gray and ductile iron, microscopy, chemical analysis, defect analysis of cast iron, and thermal analysis of cast iron. Now the floor is yours, sir. Thank you.
Thank you, sir. Thank you. Thank you so much. I think
Veera, sir, 1 minute. Shekhar, please ensure everybody is on mute, and all the guests who have joined our webinar, please ensure you are on mute so that we can have a very fruitful session. As Veera Vignesh is very knowledgeable person, highly technically skilled, so we would like to get an uninterrupted knowledge sharing session from him, sir. So we request everyone to please make yourself on mute and let us enjoy the session. Any questions, please post in the chat or raise your hands, and if the speaker wishes to address the questions in the middle of the speech, we will go for it, or else at the end of the session we can address it. I hope it's okay, sir. Veera Vignesh, sir.
Fine, sir. Thank you, sir. Good afternoon, all. It's almost going to be an evening, and it's a Saturday evening, so I thought, okay, this is the right time to pitch in a lot of information, lot of sharing, because we are almost exhausted. We have almost exhausted our entire energy for this week, and now I think our mind will be a bit free to take in some inputs. And I thank the Institute of Indian Foundrymen, particularly Chennai Chapter, the Southern region, because I have got lot of benefits from attending these kind of webinars, and now I have got an opportunity to present my thoughts and then the experiences which we have gathered so far. I thank the entire organizing team for creating such knowledge sharing platforms. Thank you. And today's topic is going to be dive deeper into your foundry defect analysis. And so today I'm not going to talk about much of technical. So it is not going to be chemical reactions, physical reactions. Rather, I'm going to talk about how you should approach a defect, or how you should handle a defect, and how you should maybe the one best or possible way to solve a defect. So in this presentation, as you know, root cause analysis, we keep hearing this from customers, suppliers, every individual, our higher ups, our junior people. We have told this hundreds of times during our working scenario.
Hello, sir.
Sir?
Yes, sir.
You have anything? You have a query? Hello?
Do
You
you have
can
any
continue,
question,
sir.
ma'am?
Okay. So this root cause analysis is always been a mystery, and this continues to be mystery because there are some things called unknowns and unknowables. So we sometimes feel for the comfort of ourselves, we keep the unknowns as unknowables. So let us try to unfold some of the unknowables today, and let us understand the casting defects, and we'll try to sort all these defects. We'll have some
number கொடுத்திருக்கேன் சார் கால் பண்றாங்க அவங்களுக்கு
on the
okay.
We'll
Shekhar
be
sir, please make sure everybody's on mute. Sorry.
Thank
sir.
you. Thank you, sir. Thank you. And we'll be going through some knowledge, like what is the importance of having knowledge of the defects, and a suggested or an approach or a methodology to handle a defect, and always ask the right questions. So we'll be going through these are the gist which is about to come today. And root cause analysis, the mystery. The reason why we call this mystery is because, see, it is mostly considered to be person perspective. Say, for example, I think that this problem is caused by this root cause. So I start becoming confirmation bias. See, the word confirmation bias means, so I decide that this is the most possible, or this is the most favorable thing which I decide with my intellectual knowledge. So I try to gather or grab all the information justifying that statement. So if I do a root cause analysis, then I think if what I think as the best cause becomes the major cause. If somebody else does the root cause analysis, what he or she thinks as the major cause becomes the most important cause. But it is actually not that, and because the defect is not person sensitive. And the casting process, because the casting process involves lot of science inside, lot of mathematics inside. See, a lot of chemical reactions, lot of physical interactions happening during solidification, during pouring, and the entire process scenario. So there is a lot of complexity in the process. That is the reason why arriving at a proper root cause to solve a problem is always becoming difficult for any foundryman. See, if people have started their career as a recent foundryman, they find it very difficult because there are the complexity in the process and the basic knowledge what they lack or what they have not acquired is making it more difficult for them to understand what is the defect and then take action. And see, you have to understand the defects first. Say, for example, when you want to solve something or when you want to set something right, then you should know what is that actually. Sir, I'm getting an echo. Okay, thank you. So casting defects are always very difficult to characterize because, see, again, it's person sensitive or experiential knowledge sensitive. See, I say this as sand inclusion. Okay, I'm the most experienced person in this organization. Okay, I expect everybody else to just listen to me, and everyone should call that as sand inclusion only. Or even if somebody else have got a different thought, I don't expect or I don't encourage them to come up with their difference of opinion, telling that, sorry, sir, I differ from you. This might be a different thing. Or other way, with the experiential knowledge, what I've gathered so far, I always categorize whatever I look or whatever I want to classify it as a defect. So I always categorize in the same way. Say, for example, anything looking dull, I can call it as a short pour or a cold metal, a cold lap. So I try to characterize the way I know. But the problem is most of the defects are not just due to one cause, or it is not just one defect. It is not just one defect, one cause causing one defect. One cause might be causing multiple defects. There can be 2 or 3 defects combined together. One defect could have led to the formation of the other defect. So categorizing a defect always makes the first challenge. And if we don't categorize the defect, we'll not be able to understand the defect. If you don't understand the defect, you will not be able to take the next step to solve the defect. Most of the defects generally fall into 1 or 2 categories. There are some similarities, there are some dissimilarities, opposites, what we call. So it is always best to understand the defect. So to understand the defect, first you should be knowing to categorize the defect. So we can make a major classification between the defect. So I'm not going to talk about sand defect, mold defect, metal defect. No, any defect which is coming up will be categorizing as a chronic defect. That means which is long-standing, which keeps coming every time, or a seasonal defect, or it's a long-standing defect, or it is for a quite amount of time. It is prevalent for a quite amount of time. But the other defect is random or uncommon. So we always make a wrong assumption that some of the random defects are chronic defects, and it is expected to happen again, and we start considering a random defect as a chronic defect. Sometimes you should just let the defect go. Maybe the next immediate day the defect might disappear, but that does not mean you should not do a root cause analysis. But the way you treat a chronic defect, the way you treat a random or an uncommon defect should be different. So standard set procedures to be arrived at, because chronic defect is generally time bound, seasonal, a particular process related, but random is not that way. But both of it should be, both of these defects or defects of these categories should be addressed in a different way, but with a set procedures. So if a defect occurs, measures must be adopted to eliminate its cause and prevent its repetition. So that is the baseline with which we should start any action. Say, for example, I should not look at a short-term solution. Today, if I get rid of this defect and complete my production target, say I have to make 1,000 castings, I have to supply 100 tons of castings. Okay, my today's problem is solved, so I'll take a shortcut. No, because when you take a shortcut, it might look like a small a patchwork being done to the defect, but it might open up in a bigger way, which is, say, for example, tomorrow you might be looking at a bigger process change, or tomorrow you'll be looking at a different trials you would have been planning that way, or you'll be having a foreign visitor coming up, you'll be having your MD coming up. So,
sir, you're on mute. Please make yourself on mute, sir.
okay. So if you don't have a thought process of understanding the cause, determining the cause, and prevent the repetition of the defect or occurrence of the defect, what happens is you start taking shortcuts and you work for today. But actually, you should not be working for today. See, we think that the short-term solutions are very easy to take. So I'll do a small patch up and then I'll try to cover up today. Because when you try covering up today, one defect, see, there is a simple term. Defect is an effect of, like what you say, defect means it's a compounding effect. So say, for example, today you had a defect, you have a problem in with respect to SAM temperature. Say, for example, your retention temperature has increased today. So today you try to add some water, control or reduce the SAM temperature for just the day or for just the shift, and you run your foundry. This increase in SAM temperature might lead to some other defect, like less strength in the mold, leading to erosion in the mold while filling. So you start getting sand inclusions, then you start getting other related defects. The strength of the mold comes down, very remote location shrinkage can come up. So one cover up can lead to multiple defects. So we should always target in understanding the cause of the defect, eliminate its cause, and prevent its repetition. So some more things about the random or sudden defects. So there are two journeys you should be taking in sporadic defects. Sporadic means uncommon or random defects, because chronic defects are, okay, say for example, my during monsoons, my humidity in the air is going to be high. So my moisture content in the mold is going to be high. So there is a high chance of all gas related defects. So I take special action such that I keep my moisture in the mold less, and I preheat my ladle more, because there is going to be loss in temperature. So chronic defects, with experience, with learned knowledge, with textbook knowledge available, okay, we can to some extent attack or control the chronic defects. Because see, when the monsoon starts, okay, I have an action plan. So when the monsoon starts, I have an action plan already ready. Okay, I'll preheat my ladle twice. I'll reduce my moisture. I keep at increased intervals. I keep checking the moisture content in the mold. I keep checking the permeability of the mold. So I've got action plans. But this uncommon defect, I do not know. It might happen today. The moment I leave my foundry, my operator or the second shift or third shift operator might call me telling that, sir, suddenly a defect has occurred. So this random or sudden defects, we have got two journeys. First thing is diagnostic journey. That means you should understand the symptom, and then that some symptoms should lead to a cause. And the second journey is the cause to remedy. So if we try skipping the first journey and then directly go for the cause to remedy or directly to the remedy, then it is again the biggest mistake we might be doing it. See, as I was telling previously, one defect is not just one defect. It is a environmental, for example, that is a system. Let us consider that as a system, a casting as a system or a process as a system. That system has responded to the environment available. It can be a mold, it can be a core, it can be a casting, it can be liquid metal, it can be inside the furnace or whatever be. So there is always a temptation to attempt to diagnose a defect by possible causes. So what happens is we always have some basic knowledge or basic understanding with the experience what we have gathered so far or what we have learned from people from our higher ups. So we try to put or we try to fit all the defects with only the causes we already know. So what happens is with your limited knowledge, you start attacking a problem. You always think that this is the only solution available for that particular defect. And you keep trying the same thing again and again, but still the defect might reduce or might not reduce. But after taking so many iterations, you think that, okay, this defect cannot be solved. So this is the maximum capability of this foundry or a process. So I have to live with this defect. See, these things come up because you have done an incorrect diagnosis of the root cause and or you have done an incomplete or incorrect remedy of the problem. It is because your root cause analysis or the knowledge available to do a root cause analysis or diagnosis is insufficient. So it is always important to identify the symptoms properly before you assign the cause of the problem. That means you understand the defect first, you feel the defect first, you see how does it look like, what is the shape. That is what we're going to see in subsequent slides. So this is the target for every foundryman. So it should be 0 rejections and 100% okay castings. So how do you achieve this? Identify the rejection, eliminate the rejection, and control the rejection. So these are the three things which we'll be keep talking again and again in this entire presentation. So knowledge of the defects. So it is the same scenario, PDCA, plan, do, check, act. So to make okay castings, you would have done a planning, you would have done you will be doing something, making the process, you check the you check the correctness or promptness of the process, and then you produce, you sell, you make the castings and you sell. In the same way, you should have a plan, do, check, act scenario for defect analysis. Before even you starting getting a component or starting a process, you should know the list of problems that can come up and what all are the problems related to the process, related to the product, related to the material, which we generally call as FMEA. And for every defect which is about to come, the knowledge should already be available in the foundry. It can be a resource, it can be a person, it can be in the form of a textbook, or it can be in the form of charts available. But knowledge of the defects should be available in the foundry, because without the knowledge, you will not be able to diagnose the symptom. If you don't diagnose the symptom, you always take the wrong step. And it is like going to a mediocre doctor, taking an injection to solve all the problems. Before, say, for example, you would be having, you would have been starving for 2 days, 3 days, you would have got some ulcer, and that could be leading to some other problem. But you go to a mediocre doctor who is less experienced, who does not diagnose the problem in a right way. See, he gives you injection, something like that, telling, okay, I give you 1 injection or 2 injections or a heavy dose of medicine, such that for time being you forget the pain. Maybe for time being you might be forgetting the pain. But what happens? The root cause of the problem is not addressed. So it might occur again at the same magnitude or even a greater magnitude. You might be having some side effects also. So you should, before starting the investigation of casting defect or any rejections for that matter, you should start understanding what is the nature of the defect. How does the defect appear? How does it appear? In the sense, it is not just by naked eye. You have got different views of looking at a defect. You can use a magnifying glass, you can use a 20x microscope, you can use optical microscope, which can go up to 1000x. You have got scanning electron microscope, which can go up to 1 lakh x. So how does the defect appear? Possible location of the defect. So where are all the defects located in the casting or in the process? It is particular to this location, or it is particular to this location, and mechanism of defect formation. This is what is the knowledge gathered. So if you don't understand how a blowhole is formed and what are all the causes which can lead to a blowhole is a gas defect. So where is the gas coming from? Is the gas coming from just the moisture? Okay, if there is a non-green sand system, but still there is a blowhole, we should be having a mechanism of defect formation. That means whenever you start doing a PPAP or a FMEA document, you should have listed the all possible defects and the mechanism of every defect with which it can enter your foundry. Say, for example, a no-bake foundry need not worry about moisture content in the sand. May not be worrying about moisture content in the sand because the no-bake foundry might not be having a green sand and there is no water additive. So that may be the least cost, but you should not eliminate it because during monsoons, even that kind of no-bake mold fixes moisture. So it is not the moisture being added to the mold, but moisture absorbed from the atmosphere. So this foundry, like an no-bake foundry, gives least importance to moisture, and the green sand foundry gives more importance to the moisture. So like this, the defect formation or the mechanism of defect formation, all possible kind of defect formation should be already available with the foundry. If not available, we should make it available, because without knowing that, you should never start making a casting, because if it is like getting it, like folding your like closing your eyes, folding your hands and getting into a say for example walking in a path which you do not know what is going to come up. So during the investigation phase, you should always ask the right questions and more pertinent questions. So you should keep asking questions again and again until you get the maximum insight available. Okay. So let us come to a typical methodology to approach a solution for foundry defects. So you have identified the problem, you identify the problem right. See, the problem identification is the first step. And who identifies the problem, how is the problem being identified, plays major important role. So the first thing is you identify the defect or you identify the rejection, then you write the problem description. Any wrong identification or any problem description leads to a different scenarios. A problem description should involve every aspect of the defect. When did the defect come? When was it found? How much is the defect? What is the severity of the defect? In how many places it has occurred? Since when it is observing? So a detailed description of the defect. You would have seen some reports of doctors where you have got a small summary. It takes up everything. Say, for example, you meet with a small accident. Hopefully nothing like that should happen. You meet with a small accident, you go to a doctor for a first aid, and the doctor starts asking you where you're feeling giddy, are you feeling a pain in any of your like upper head, or do you have any bleeding happening from your ears, or you have any breathing difficulty? So these kind of questions come up and they record everything. The report will tell that, okay, this person came at 9:39 a.m. These are the questions asked. These are the answers given by the patient, and it will be recorded. So such kind of detailed description of any problem should be available, because you cannot solve the problem on your own. You are going to have a team where the description is to be understood by the entire team, and a group of minds are going to work in solving a problem. If you think you are the only person who can solve all the problems, that is not possible, because if you start thinking in that way, then you become the biggest problem in solving the problem. So the problem description is to be made in such a way that anybody who is going to become a part of that problem solving team is going to understand the exact picture the way you have understood it. Okay. Next comes the interim contain actions. Okay. So you have identified.
Doesn't appear, sir.
So next comes the containment actions. Okay. A defect has occurred, you have identified the defect and you have made the probable description, everything is available. So, but you should act immediately, because you cannot keep your process continuously producing rejection. You take a interim containment, you stop a pouring or you segregate all these castings. That is just to ensure that the further processed item is not getting affected. So that is not the solution. You understand, removing this defect or slowing down the further causing of defect is not the solution. So this is called as containment action. Say that, for example, you found say for suddenly very high magnesium or a poor nodulity you have identified in one particular pouring. What you do is you immediately cut down, you move all the castings outside the line so that it does not get mixed up. Sir, I request all the participants to mute
Shaker,
yourself.
please check all the participants are on mute. If they are not, please just mute them.
Thank
They
you.
are
Okay.
not.
Okay, sir. Okay, sir.
Okay.
Members,
Then
please mute yourself, sir.
Yeah. So after you have to take interim correct containment actions, that So interim containment actions are, you can remove that problematic items from the system or the process such that it does not cause further rejections, because any rejection is going to cost to the company. And this containment actions depends on the type of rejections and the decisions which the organizations can take. Say, for example, they can stop pouring, they can shut down furnace. Some people would not be able to shut down furnace, so they can slow down the melting or make some course corrections and then they continue the melting. So they can scrap some molds, remove castings from the line. So these kind of containment actions can be taken place. And this is not the solution. And this is not even called as temporary solution. You contain something such that it does not grow further. Next comes the root cause analysis. Only after doing a containment action, then with the identified defect, with the description of the problem available, you should start doing root cause analysis. And there are a lot of tools available to do root cause analysis. This 7QC tools are available. Maybe you can use a like Ishikawa diagram, which is called as also called as this fishbone diagram. There are many methods of doing it. You can do why analysis, and you keep asking why has this defect come, why is this, why is this, why is this, and finally you arrive at okay, fifth way or sixth way, you get satisfied, and then you start working on it. And again, what happens is root cause analysis. In root cause analysis, you'll be getting lot of possible causes. A person with a different mindset or setting a core inside, or person who is not so obedient or not so attentive in handling things can also become a root cause. But you should do a funneling operation after arriving at the list of root causes, and you should start doing the elimination processes that you arrive at maybe 2 or 3 or 4 major root causes, and then you keep experimenting those root causes, finding out whether there is a change happening in the system because of the change in the causes identified. Then you have arrived at some 2 or 3 root causes or 4 root causes, and I have to caution you that the root cause analysis may not lead to just one cause, because it's a process industry, and it will not be just one person or one cause creating the biggest defect. So it is a combination of 2 or 3 causes or 2 or 3 systems or 2 or 3 part of the system creating one defect. So the root cause analysis might not lead to only one cause. Okay, after you have done the proper root cause analysis, you have taken some corrective actions. So corrective actions means implementation of the causes, implementation of the actions to subdue the root causes which you have identified. Then you identify and implement the preventive actions. So corrective actions is to ensure that it does not happen in the existing system. Okay, preventive action is such kind of defects never occur in my company or in my organization. So that is the next preventive action. So corrective action means maybe I'll do a double check of my casting before sending it to my customer. Preventive action is I ensure that such kind of defect does not come and I don't need to do a double check. See, I'll do a preventive action, and then I'll implement the preventive action. Then after implementing the preventive action, all these actions are time bound. You should have a review mechanism. Please don't come to a complacency level that, okay, I've taken an action and the defect is not going to come forever. Because with the knowledge available or with the limited information available, you would have arrived at this preventive action is the major problem. But what if it fails in 1 or 2 months? So you start monitoring it over a given time, and then that is called as effectiveness measure of the preventive action. You take a look, if it is okay, then the problem is permanently resolved. If the problem is permanently resolved, yes, document it. If you don't see the problem permanently resolved, then you have done something wrong in the identification or root cause analysis. When you're doing a effectiveness check of the preventive action already taken, and if it is not so effective, then you have done something wrong in the corrective action or in the root cause analysis. So this is a loop, and this is a time bound loop, and this process should not stop. So then you should ask the right questions. As we were talking about in the previous slides, you always ask the right question. Where are the defects? The defect is on the drag side or the side walls, or it is above the core or below the core. So you try to understand, you try to take the technicality or the appearance or the location of the defect such that you will be able to stratify the defect, as we were discussing previously. If you stratify the defect, you can categorize the defect, and when you categorize the defect, you can easily arrive at a root cause. Are the defects found at the same location? Are you getting the defects continuously at the same location with the rejected castings or rejected process items? Are the defect occurring all the time? So is it a chronic defect or a non-chronic defect? Are the defects people related? Say, for example, the defect has arrived at a place where more laborious work is happening. So a lot of people involved in that operation or a process. And are the defects time related? So has it happened in the daytime? Has it happened in the night time? Is it related to seasonal changes happening during monsoons or not, or the defects cavity related. Say if my casting or a mold has got multi cavities, is it particular to it? So you should have a defect pattern or defect defect severity or defect occurrence. Without that, you should not start doing any kind of analysis. So do these occur in similar jobs? So this is horizontal deployment and horizontal checking. So if you want to check whether such kind of defects have occurred in another kind of castings or similar kind of jobs also. So you study related to the defect. So you start asking questions related to the defect. You start asking, see the question you should ask the process, not the person. Have you done this mistake? No, that is the wrong question. Has anything gone wrong in the process? Okay. Has the SOP been not followed, or there is no SOP available, or the process or the guidelines available is not sufficient enough. So these kind of things should be also considered when you start diagnosing a defect or when you start analyzing a defect. And are there related defects occurring? Say for example,
for run slabs that is how you standard again. You end the contract.
Sir, I request. Yes, thank you. So there are some related defects. Say for example, misrun, short pour, runout, slabs. So these are some kind of related defects. So rat tails, buckles, scabs. So you see either one defect or its related defects available. So when there are related defects available, then you can identify that as a clue available already. So where you can easily arrive at a root cause. Say for example, you get a scab. Scab is a penetration defect. When you have a penetration defect available, sir, I request let me complete the presentation and we'll take the queries further, sir. Thank you. So when you have any related defects available, say for example, I was talking about a scab. So when you have a scab available, and if the scab is of an erosion type of scab, then you can definitely. Sir, requesting to mute yourself, please.
It's very disturbing, sir. Please consider his time. Please mute yourself. Shaker, without any questions asked, please mute everyone. You have the permission. You have the access. Please mute the participants if they have by mistake switched on the mic. All questions, as as sir said, will be asked in the end of the session. Okay. Thank you.
Thank you, sir. So, say for example, I was talking of an erosion scab. So if there is an erosion scab and it is a penetration related defect, and if there is an erosion happening, then there is a very chance that eroded sand particle would have got settled somewhere inside the casting. So if you see an inclusion in the casting, a sand inclusion in the casting, then you start analyzing the root of the sand inclusion, and it might lead to a scab. Or if you're finding a scab in the casting, then you should also look for a sand inclusion in the casting, because one defect might have led to the other defect, or these defects might be related to each other. When related defects occur in the castings, it may be an indication of a system related issue, might be a related issue. So I think it happened for me to go through an Indian standard which talks about controlling the foundry rejections. So there is a standard available, guidelines for controlling foundry rejection. It mostly talks of gray and castings, and it is the standard number is IS 1288801989. It is available in the internet, and anybody can download these things. And what does this guidelines tell is, it has already talked about the attainable foundry rejections which is possible. As Kumar sir was talking about the rejection levels in the start of this presentation, what this standard tells is attainable foundry rejections is 5% max. Attainable machine shop rejections is 2% max. Of course, this is pertaining to gray and castings, but this talks of a process of handling the foundry rejections. So it is giving you some indication of achievable rejection levels, and it talks about how, on what basis you should be reporting a rejection, and the reporting rejection system it talks of, and it talks about what is the method card and how a method card should be and what all it should contain. Then it says how should a rejection meeting be conducted and who should conduct a rejection meeting. And it also talks about the feedback system after the rejection meeting, training of the personnel, suggestion scheme, and statistical control. What this else is, even if after having a rejection meeting and you have a feedback system, but still the rejection is not solved, it is like this: you make a bounty, and you tell that, okay, somebody who is solving the problem will get a prize. So you can have a suggestion box even to solve a defect. It need not be just the core team available. And what it talks of is training the personnel. The exact lines which is mentioned in the standard is workmen, supervisors and managers shall be required to undergo suitable technical and managerial courses to keep them up to date on the subject. The subject means controlling foundry rejections. Such courses shall be either organized within the organization or by different educational or professional bodies. So I think that is what is IIF right now doing it. Thank you. And what happens in the rejection meeting, or how should a rejection meeting be conducted, is the meeting shall be conducted by either the chief or quality control or troubleshooting unit, who shall properly identify the defects decided on the unfinal status or the rejection. That means you should not conduct the rejection meeting before identifying the defect or before deciding the defect that it is called as so and so. So if you don't identify the defect, you should not even conduct a rejection meeting. This is what the standard tells. So I think it is better. This standard has been arrived at so many iterations with so many thoughts coming up. So if we just go by the standard, you understand the defect, you identify the defect, you name the defect, do the problem description, only then conduct a rejection meeting, because only then you will start getting the fruit of the meeting. So identification of the defect, because this is the most crucial step. You should have the right analysis tool, or you should have the right analysis measurement, or that will lead to a control on deviations, and that can lead to a less rejections coming up. So what is available, the different types of analysis generally being conducted in foundry, one is subjective and the other one is objective. Subjective is generally by experience. See, with my experience, okay, when I feel this casting, or when I touch this casting, when I touch this part, it looks like something rough surface for me. So this can be a burn-in defect or a burn-on defect. So that is by experience. Or you use some scientific tools. Given an example of a spectrometer or a microscope, but you have tools to measure any. If you have tools available to measure, then it can be a quantified measure, and that can become an evidence of the analysis or the identification of the defect. Factors which can generally influence the subjective analysis is eyesight. So the way I see or the way I feel generally decides, or generally tends me to decide what is that defect actually. And positional hierarchy. Sometimes, as I was telling previously, if my upper boss generally tells this as a defect, I sometimes or sometime I somehow feel that, okay, I don't want to defy my boss, or I don't want to defy my upper like person who is above me. So I just go by his words. Okay, let me try the way he has already told, or he has already decided. Okay, might be the way that person or the junior would have identified the defect in the right way, but it is not coming out. Okay, environmental conditions, see, illumination, or the way you analyze the position where you keep yourself and analyze matters a lot. Skill level, because training on identification or the classification of defects, that means you should have already forecasted that such kind of defects might come up, and I should have already trained my workforce available to identify and classify the defect. If that is not there, subjective analysis will always be biased, and it can lead to a wrong defect identification. To avoid misleading identifications and conclusion based on subjective analysis, subjectivity is actually to be removed by objective method. Anything a person has got something to tell about the defect or something to tell about the process, make a platform, make a quantifiable measure, and then let that be measured, and let it be documented. So it should not start as, I feel that this is defect. No, I've analyzed that, I've done a chemical analysis, and this shows like this, and because it is showing like this is the defect, or this is how I've identified this defect. When in doubt, please ask. When in doubt, please do not conclude. So the category of analysis generally conducted, you do a chemical test, you do a metallurgical test, and you do a mechanical test. And this classification is generally related to liquid metal or castings. And a similar kind of general analysis also happens to sand or other raw materials also. The chemical, then you do a chill wedge test. Maybe you can use this chill wedge test with the experience to arrive at the carbon equivalent, maybe in the past, but right now we have got good spectrometers and other techniques available. And you have been using CE meter, use wet analysis, use spectrometer to do the chemical analysis, and you use the same chill wedge to predict the microstructure or look at the chilling tendency available. Use optical microscope to analyze or study the microstructure of the castings. Then mechanical testing, you do only hardness, or you do hardness and tensile. you do impact, tensile, yield distance. So all these properties you measure. These are the general things which is available in a foundry to do analysis. So what is generally analyzed in foundry is, sorry for the mistake, the typo error in hardness, it's just double S only. And what is generally analyzed in foundries with respect to liquid metal and casting, if we talk of chemistry, you measure the major elements, sometimes trace elements also, but most of the times not calibrated. And metallurgical microstructure, we look into the graphite shape, size, matrix, and carbides. Okay, mechanical, you check hardness, tensile, yield, impact at room temperature. Some, if customer requirements are there, impact at low temperature also. So these are the analysis already available in customers or in the foundry. Even after having so much techniques, so many quality control, so many levels of checking available, why are the rejection rates still high? So what does it actually tell is, maybe the existing analysis tools are not adequate enough, or not competent enough, or what you say, not to the level to identify or diagnose the defect which is coming up. The identification of the defect or the issue is not done right way, or the deviation is not measured in the right way, or it is not being used in a proper way to control the deviation. So what you can do to get over with this is, there are advanced techniques available. Say you can do EDAX, or see, with respect to chemical composition I'm talking of, you can do a cross check sometime using LICO, carbon sulfur analysis. You can use a cross check of this with your existing spectrometer, with your existing CE meter, with your existing methodology of arriving from the chill wedge leading to a carbon equivalent. You can have a cross check of all these things. You can have a cross check of your OES analysis. You can have a cross check of your electron microscope. Because the reason why I'm emphasizing on the analysis technique is because these analysis will lead to a number or an attribute, yes, no, or some numbers. Using that numbers, you identify the defect or you stratify the defect, right? And if the defect stratification is done right, and you have got a measure to measure the defect, then you will be leading to a proper corrective and preventive actions. So these are the different types of advanced techniques available generally with respect to castings, which can help you in addition to your existing analysis. So I've got two case studies with me right now available. So I'll share with the experiences which I had faced, and we have overcome those experiences right now. And I'll talk about the wrong identification of the defect. See, this is the defect casting piece which has come to us, and for an analysis. And it was written previously when the sample was received by us, telling that this is that slag inclusion defect which you have arrived at the foundry. So I want you to analyze what is this slag. So this is the problem statement given by the customer with the casting sample. Okay. So what we do is we start with the micro analysis. So because we do not know what is the grade of this material, so we wanted to understand whether it is gray or ductile. So we did a microstructure analysis. Yes, we have done a conventional microstructure analysis. One near L1, that is the location which is marked, and L2. There is a small deviation in the gray castine microstructure. It is type A, predominantly type A, but near the defect location, there is a like non-uniform or not so expected kind of type A is available, and some C and chunk kind of graphics is available. This means that some solidification pattern or methodology has been affected. So what we have done is, okay, we have started analyzing this with a deeper microstructure, with a deeper analysis technique available. So what we have done is, we have a scanning electron microscope at R&D center. So we can actually look into the defect, which is deep inside the cavity, which is available, which generally is not possible in a conventional foundry. So we went to the actual inside location of the defect, and this is what is actually looking at. So when you go into this defect, you start looking at, you see the graphite flakes. These are the lines which is graphite flakes, and the marked area I've analyzed into 3 locations. So you see a ball, like a sphere, a metallic material inside, and then you see again a small spherical material inside. This is the good region which is away from the defect. So when you compare all these 3, you see iron, you see silicon, aluminum, and you see oxygen and carbon. So what does this analysis additionally tell me is, okay, this is iron only. So 87% means it is mostly iron, and it has got some carbon, some oxygen and silicon. It is not a different material. It might be close to a parent material. So since if I draw making the observations, see the defect is looking, the defect cavity has got a spherical nature inside and it is a cavity. So it is a cavity defect caused by what? So we arrived at, okay, the morphology is spherical shape, the composition is found in a similar way, and the defect is cold short. The reason why we have arrived at this is again with the available knowledge and available information. The way we arrive, the reason why we arrived at this as cold short could be a cold short is because the morphology of the defect, what is deep inside the defect is like this, and the source of the defect could be, say for example, it could be either a change in turbulence or the initial velocity could have been different. So these are the defect tools which is generally not available in the existing microscope, or which cannot be done by a conventional method. So these insights can be additionally provided to a defect analysis. So this entire new analysis which is done adds some value or adds some input to the identification of the defect or stratification of the defect. So we give additional one information. It can be a slag defect, it can be a slag inclusion, but it is not just slag inclusion is what we are trying to emphasize here. So the defect, what we have identified it as cold short. So we direct the foundry, we explain the foundry that, sir, it might be a slag inclusion or it also has a defect called cold short. So you should look at the possibility of both the occurrences, maybe what has caused both, as a cold short as well as an inclusion. So this is the additional information. So this is related to the identification of the defect. So what generally happens is when you don't, when you do a wrong identification of the defect, your root cause analysis becomes wrong, and you keep spending a lot of money, but still the problem is not solved. But when you identify the defect right, you do the right problem solving, and you eliminate the defect. So this is how a wrong identification of the defect and the right identification of the defect can lead to. And another scenario is a case study which talks of crack in the casting. So this is a grain component again, and the defect which was mentioned is I am getting a crack in the as cast surface. So this is before machining, and as cast surface there is no machining in this location. So what has happened is customer has identified a crack, they have visually seen a crack. So they wanted to analyze. So they wanted to do a metallurgical analysis. What could be the root cause of the crack? So we have done a conventional microanalysis, and this microanalysis has revealed some information to us. So you can see pockets of type C and some chunk of type C microstructure available, predominantly type A, the balance being type C. And it is predominantly ferritic, no carbides available. But when we did the analysis, we found the traces of stearates available. Okay, there is some amount of type C, some amount of stearate available. Okay, this is what I've analyzed with my facility available. Yes, this is the information. Does it lead to a crack by itself? Is the next question. Say gray cast iron might be having some default phosphorus in their system, or because of the section thickness of the casting, type C might be allowed because I do not know the customer's requirement, end customer's requirement. So I will not be able to conclude telling that because type C is identified, some stearate in trace level is identified, this will lead to a crack. So these are indications available. This might be leading to a crack, or this might not be the start of the crack, but you can let the crack propagate. See, the source of the defect is not these microstructures, or it is not evidence-based microstructures. But if the source was something else, these microstructures can let it penetrate through. So this is how your analysis should pave through, or the knowledge available, the resource available should pave through. So it is not just giving a one conclusion or one solution to a problem. You guide the people in the right way, you guide the team in the right way, such that you go into the right direction and solve the problem. So what we have understood after this report with the customer is there is a knockout happening and there is a hammering happening near this location. That excessive hammering could have caused to this, and when they removed that process of hammering and they have refined that fettling process, the crack started reducing. It suddenly disappeared. So it means the root cause of the problem is not stearate, or root cause of the problem is not microstructure type C, because that is what a typical quality person might be thinking of. The moment you do cut section analysis of a defect location, you see type C, yes, a type C is the problem, reduce carbon equivalent. Or there is stearate, okay, reduce phosphorus. What if that is the property of the metal? What if you have arrived at a carbon equivalent such that the other part of the same casting where you don't get shrinkage. You would have arrived at this carbon equivalent for a particular reason. You would have been using or following the same carbon equivalent for years together. But why did the crack arrive today? So that means you have not understood the proper root cause of the problem. So if you don't identify the root cause properly, you might be looking at altering your carbon equivalent or altering your carbon or changing your phosphorus. So this is how your right analysis or right information to the analysis people will be helping them to lead to a proper solution. And I just want to explain about the perception and advanced techniques available. So what people generally think about advanced techniques is advanced technique means it is about the analysis technique. It is about the resources available, sending for a training, investing on a training. Okay, all these things are advanced techniques. Let us call it as advanced technique. People always think that it is costly, but it is less costly when you compare it with the amount or the cost of rejection which is coming up. Cost of rejection is not just cost of rejection. It is the credibility of your name at the customer's place. Might be next time the customer is not going to believe you and he's not going to give you a repeat order. So that is less, that is more costly than the cost of a training or a cost of an analysis. People think that it is time consuming. No, it is not time consuming. It is systematic. There is a minimum time which is to be consumed by the system or the process of defect analysis to solve or rectify the problem. If you think a solution can be as quick as with just a snap of a finger, I think it is wrong, or it is not the right solution, or you're trying to cover up something. The time consumed by various trial and error method is actually a bigger time loss. Say, for example, I make 3.1 carbon, 3.2 carbon, 3.3 carbon, 3.4 carbon. That is a waste of time. I cannot do so many trials at my foundry. So I invest in the analysis techniques or advanced techniques available by a training or by knowledge gathering, such that I take minimum number of trials and then I solve the problem at the earliest. And not available at all places and cannot be afforded in a foundry. Yes, it might look like an expensive. It might look like expensive to the foundry. Sometimes people think that it is not affordable foundry, but this is just a one-time investment. If you think that this is not being considered at the design stage or at the starting stage of a process or a casting, then this is the biggest mistake any planner is doing it. So, okay, so for example, either I control my process or I forecast that these defects are going to come up. So I make my process so strong and then so controlled. Or if I'm ready to start my process lethargic, then I should be ready to invest in some kind of these things. So, and again, all foundries need not have a scanning electron microscope. All foundries need not have a radiography technique available. So there can be one location where only when the defect comes, it can be sought for, and then you can just get the confirmation done, you can just get the analysis done, and then you can solve the problem. Only if the need arises, you're going to invest. And this, as I was telling in the first slide, it is not costly. And interpretation capability of the results by foundrymen is not available, or it is difficult. Sir, everybody should develop the intellectual knowledge, or we should keep updating ourselves. The root cause analysis for the blowhole defect 10 years ago, 15 years ago could have been different, and with the knowledge available today, it should be definitely different. It should be more refined. You should be able to pinpoint all the defects or all the causes possibly. We should be able to list down all the causes possibly, because the world is growing, and you cannot tell that no information is available today. And always a third eye perspective will give you a new scenario. It might confuse you or it might guide you in a different way. So it is all sometimes better to have a third eye perspective. That means getting a done analysis outside or inviting somebody to add value to your process of rejections handling. So what I've done is I have some questions, 4 or 5 questions, which I thought, okay, so let me understand the existing scenario of a foundry. I've made a poll. I'll copy the link of the poll in the chat box, and I request all the participants, if they wish, and there is no confidential details in these questions. So I request everybody to wholeheartedly and true to your knowledge respond to this question, such that we'll understand where are we. So the first question is, do you have a defect or rejections handling procedure and guidelines in your organization before the start of production? That means when you take up the casting. And the second question is, how many times during rejections handling have you adopted a proper and systematic approach? Say, for example, out of 20 times, I would have had 10 times, I would have systematic approach. I'm not going to tell that you're not systematic at all. Out of 20 problems, 10 problems I would have spent in a systematic way. 10 problems I would have taken a shortcut to solve because I didn't have time. So how many such instances are there? And how many times have you achieved first time right in solving defect? So you tried to solve a defect and you solved a defect permanently at the first time of trial itself. How many times have you solved the defect and you have created another one? Say today, to reduce the weight of the casting, I've done some exercise, or to increase the flow rate or filling, I've increased the ingot thickness or some kind of gating thickness corrections I've done. But because of this, I've created an inclusion. So how many such kind of occasions you have had? And how many times have you documented a defect analysis approach followed? Say you would have already followed a procedure or an approach to solve one defect. Do you have the documentation available with you right now for future reference? So I give you 10 minutes. I'm going to post the link in the chat box, and I request all the participants to fill their proper feedback and true to their knowledge, such that we shall discuss with those information available. So I think I've copied the link. It's 15:30, that means 3:30. And maybe I'll give you 10 minutes or 15 minutes, and I've come to the end of my session. So with these poll results, we can start taking up questions. After these results, I've got 2 or 3 slides, such that we'll sum it up and then we'll close this. I hope everybody are able to see the link in the chat box. If you have any difficulty, please ping me. I'll copy it again.
Just reminding again, sir has given us 5 to 10 minutes for us to just fill the form. So please make sure you're able to click the link and open the form and fill the details. As mentioned by him, we'll wait for 5 minutes so that everybody fills the form.
So we have almost 86 participants. Leaving me, I'm 85. So I hope this polling touches 100%, because the more the number of samples, better the statistic is.
For those who are viewing the session through conference halls where you have multiple members viewing through one link, each of you can copy the link from the chat and circulate among yourselves and enter the form as well. It will give us some more detailed information.
Thank you, sir. We'll wait up to 3:45, and at 3:45, I'll whatever is the existing results, I'll share with you. I've got so far 20 responses, so at least 50% of the entire team group of members, 40 at least would be a good number to show.
Sure, sir. And those of you who have already filled the poll, feel free to type your questions in the chat so that we can easily address it one by one, so that there are no repetitive questions.
Mr. Arul Kumaran, you had mentioned that the form is not opening, but I think people are filling it. If required, I'll copy the link again. Maybe you can use this link.
Maybe even you can copy the link and open it in a browser if it is not opening automatically.
Sir, voice is not clear.
Sir, I was not speaking at all. I'm waiting for the poll results, maybe for 5 to 6 minutes. It's already 3:40. 5 more minutes, and please bear with me. So I'll share the results and then we can discuss further. So I've got 30 responses. It's 30. It's holding 30 for a long time. So I'm just sharing the poll results, and these are the details given by you and opted by you. So just sharing this information for you. Yes. I hope the screen is visible. Okay. So the first question was, do you have a defects or rejections handling procedure and guidelines in your organization before the start of production? So if it was 100% yes, and then we are the best foundrymen in the world. Okay, we still have some backlogs. Almost 25% of the people have opted that they don't have the defects handling procedure. So it is better, maybe we shall draft something, start something, and then do something. There is a saying in Tamil, which generally just so astonishing always. Ondre say, nandre sayim, adhim indre say. That means you do something good, you think something good, and you do it immediately today itself. Okay. Next question is, how many times during rejection handling you have adopted a proper and systematic approach to resolve a defect? If everything if everything were greater than 75% of the times, okay, then that is the best scenario to happen. But what has happened is almost 45% of the people have opted that in their process of analysis, only 50 to 75% of their time, say that means out of 10, maybe 5 to 7 defects only they have approached it systematic. The rest are non-systematic. That means, see, only 19% have opted that it is greater than 75%. So balance almost put together of 60, 70, 80% around people are less than 75 times. That means out of 10 defects you have handled, most of the defects you have handled are non-systematic, or the approach you have chosen is a non-systematic method. So this is the actual scenario, and maybe this is the reason why sometimes the defects are not going off at all. How many times have you achieved first time right in solving a defect? See, if everything is greater than 75% of the times, okay, then that is the least amount of cost, time, effort spent to solve a defect. But people have opted the other way. It's almost greater than 90% of the time. 90% of people have told that it is less than 75% of their total attempts they have solved the defect first time right. That means lot of iterations in solving a defect is happening, which is going to cost you the effort, time, money, whatever we call. Everything is getting consumed or wasted, or not going to the right direction, maybe I should say. How many times have you solved a defect and created another one? So if this number was greater, 75%, then that is the most worrying situation. But only 9.7% have, that means 3 people have opted that, yes, they have solved one defect and created another defect. But if the green is more than 70%, it is more good, but it is not way. So 50, that means 25 to 75% people all put together, almost like 50% of the total people tell that, okay, I have created some defect, I've solved some defect, but still I've created the other one. Next, how many times have you documented a defect analysis approach followed for future reference? So if it's 25% each, that means only 75, say for example, only 8 people have told that they have documented the defect analysis approach most of the times. That means 75% or greater of their time. That means 7 or 8 defects out of the 10 defects they have analyzed or they have solved is documented. So the rest is 25, 25, 25, 25. Everything should become blue or it should be greater than 75%. So this is the actual scenario, and this is the reflection of what do you think and what others are able to do it. So if we want to solve all the defects in one shot, so we should start documenting. We should not create a new defect by solving one defect or taking shortcuts. We should always try achieving first time right. And if we do a proper and systematic approach to resolve a defect, and if we have the guidelines already available, then you do the first time right in solving the defect, and later you will not be producing any defect at all. And going back to the presentation, the final gist of foundry defect analysis is any defect analysis you're taking up, define the problem, stratify the problem, study the pattern or occurrence of the problem or the defect, understand the mechanism of or defect formation using the proper diagnostic tools. You should be having the knowledge or the source for knowledge already available. Investigate all the necessary conditions of the environment. Do not leave anything. Identification of all possible root causes with unbiased mindset. Do not think that if I'm a person from a melting department, okay, there is no problem in the melting. I've been doing the same melting for hours together. Okay, I think all the problems should have come from core shop or molding. If a molding person starts doing the root cause analysis, they should not bias that, okay, my molds have been good for the entire day. I think something wrong with the liquid metal. No, there should not be any bias in identification of the possible root causes. Take corrective actions and preventive actions and validate the same. Do not stop just by taking the corrective and preventive actions, you should validate the same, because if the defect is random or if the defect has got some time as the problem or season as the problem, you should be validating the preventive action taken. And the most important aspect is you should have a common sense approach. When you have a common sense approach, you always think that, okay, why did the defect come suddenly today? Why has the defect come only in this cavity? How many times have we faced this defect in this entire month? So these are the common sense approach, because you need not be a metallurgist, you need not be a mechanical engineer, you need not be a chemical engineer to start the defect analysis. You should have a common sense. And unbiased and systematic technical approach, yes, it should be there. This unbiased and systematic technical approach should be complemented by the common sense approach. Gaining and implementing the technical know-hows, because your knowledge might become obsolete and the science is generally being defined when the new technology or new principles come up. So, and because people were talking of the atom can never be broken down, and today we are talking of energy generated by nuclear fission. So if we are just to believe that atom can never be broken down, anything inside the atom can never be seen, today we are not talking of nuclear submarines or nuclear warships. So today's science can be defined by tomorrow's science. So you keep updating, gaining knowledge of technical know-hows, and you start implementing it. Use of technology wherever possible. So it is not just to eliminate people. So it is to enhance and support people. This technology will help you aid taking the right decisions or the quicker decisions, the prompt decisions. Okay. End of presentation. Thank you all for listening to this presentation almost for an hour. And I thank IIF and all the member foundrymen participants for their patience. And thank you.
Thank you, sir. Shall we take some questions? I see some questions
Yes,
from the
yes, please.
chat. So the first
Yes.
question was how to control surface finishing from Ashwin Mohit.
Yes, sir. Yes, sir. How to control surface finishing, sir? Again, I think if we go by the presentation which I had told today, the description of the defect is not so clear. Control surface finishing in what, sir? Surface finish of the core or the mold, or what type of casting, what type of sand, what type of molding practice you follow. So let us list down all these things, because if this question and if the answer was readily available with somebody, the surface finish problem could have been solved by all the foundries overnight. Frankly speaking, that surface finish problem, is it persistent to you? Has it been occurring in all type of castings? You start listing down ifs and buts, and then the pattern of it, you might be having a clue already available in your this thing, in your way of analysis. So it is not right for me to talk something and do something else.
The next question is, what actions are to be taken care for avoiding exploded graphite in SGIL?
Sir, generally exploded graphite. See, I'll tell you how exploded graphite forms. I'll just explain the mechanism. So you start having a nuclei, and then that nuclei, on that nuclei you start graphite precipitation, and then that graphite precipitation grows in the shape of a nodule. Because of the magnesium, the crystal structure available. Exploded graphite stage comes after the round nodule stage. That means explosion of the graphite has happened after it has become round. That means the first round is already available. So your nodularization process has already taken place, right? And when you start seeing exploded graphite, that means the activity of carbon is very high. Activity of carbon, which I want to tell, maybe it is easy to understand, is you have got more carbon available, for which the energy available is not sufficient, or you have got lot of activity of carbon, lot of active carbon available. That means more carbon, more energy available in that area. So you try altering your carbon equivalent to the section thickness you are operating. Say, for example, if you are operating at a thick section, you might not need very high carbon. You should optimally reduce your carbon, but please do take care that reducing carbon will have solidification related effects also. If you have been having a shrinkage in a remote location, if you have been having a carbates in a thin section casting, or if you already have hardness on the higher level, your machinability is okay. Reducing carbon will make all these processes worse. So arriving at the optimized level of carbon for your casting will take care of these scenarios. Thank you. And answering to the first question, controlling surface finish, sir, please understand the interaction between the mold and the metal. So understand the molding process. Is there any irregularity generally generated by the molding process, or is it particular to one particular heat or one particular day or one particular casting? If you start eliminating one by one, which is causing the surface finish defect, maybe we will be able to identify the proper root cause and solve the problem.
Okay.
Next question is.
Next question, could you please share?
I think it's from JMPI.
Yes.
Sir, how to control pinhole defects in flaskless molding line? Again, sir, since when is the pinhole defect coming up, and where is the pinhole defect coming up? It is coming along the parting line, coming closer to the mold. Sorry, coming closer to the parting line, or coming only on the top edge of the casting. That means which is closer to the pouring cup. And pinhole is a gas defect. So gas is generated somewhere, or the amount of gas generated is already defined because of the volume of the metal or the surface area of the mold, but you do not have sufficient venting capability to take away all the gases available. This can be one reason. So maybe we should be looking at venting. Before doing anything else, you just list down what all the changes you have done in your system, in the liquid metal or in your core or in your mold, such that which of these actions would have led to generation of more gas. Say, for example, if you had added more binder or more catalyst to fasten your curing process of your core, it means more amount of gas generation tendency is imparted into the system. If such kind of things happen with the existing gating system, with the existing vents available, you will not be able to take away all the gases. Or if you had increased your mold moisture content for some reasons, then that would have given more gas or more interaction with liquid metal, where your permeability of the mold is not sufficient enough to carry the gases away. So that is what we should be looking at, sir. The source is, see, pinhole is a gas defect, and the other way around. Pinholes are generally surface or subsurface. If it is subsurface, then the solidification is faster in that location. Please do look at why the solidification is faster without letting the gas go out of the casting or liquid metal.
Okay, here there is one more question from Balamurugan sir. How to control GD defect in SGIL?
Gas defect in GD is I think it is gas defect, right? Or I'm not able to understand it. Sorry, I'm not familiar with that context. GD means I think it is gas defect, or maybe Balamurugan sir can expand it.
Balamurugan sir, can you clarify? Is it gas defect?
Yes, sir. GD is gas defect, right?
Balamurugan sir, can you clarify?
Okay, we'll wait for his message. We'll take the next question and then answer.
Hello, sir.
Surface finish.
Hello.
Yes, sir.
Hello, sir. We are from Amarun Foundries.
Yes, sir. Please.
We are getting a blowhole in bottom, top, side wall, all locations.
Okay, sir.
It's like an little in a indenter, ball indenter in a hardness, like round shape. In all locations,
okay, sir.
Cope, drag, near ingate, and all locations we got it.
Okay, sir. Let me explain. Maybe if it is difficult, you can write to us separately. Maybe we can still have an interaction, because I don't want to waste everybody's time. People here are available. Sir, if you are getting this pinholes or the blowhole defect throughout the surface of the casting, then you have got an excessive interaction between the sand mold and this particular type of casting, or the venting properties we might be looking at, or what to say, there is lot of gas or the permeability of the mold available. I hope the mold is green sand. If not, if it is a different sand system, maybe more of gas generation is already available in the system, because generally dissolved gas content in the liquid metal is low. It is not very high the way we think. What happens then for this all these gas is liquid metal being filled at a very high temperature reacts with the atmosphere. That means core or mold or whatever be. So it starts generating lot of gases, while it is heating the mold, while it is reacting with the core or whatever it is. And when these gases are not taken away with the next immediate layer of the mold available, that means your mold should be permeable, your vents should be permeable enough such that every gas is taken away. Or there is a gas flow analysis. Generally in simulations people do, like the way they do this solidification or flow of liquid metal analysis. So if the gas is not going in the way it is expected to be, any amount of gas generated stays inside the cavity only. Say for example, if your venting system is such a way that the gas has to go against the filling of a liquid metal, gas does not have enough pressure or density to get passed through the liquid metal. Gas will not be able to pass through the liquid metal because the density is very less. So if your venting system is such a way that it is far away from, or it is disconnected, say for example, gas generates at different parts of the liquid metal and all the gases will have to get expelled at different locations, or all the gases have to combine to a single location and then go through a common vent, it is generally not possible. So wherever possible, we should be able to provide vents such that the gas generated is taken away. And the vents can be slightly over designed because you will not be able to predict how much the gas is coming out from the liquid metal. Though we have got analysis, gas analysis, core gas determinator, all these tests available, the environment is not what we is not in the way we predicted actually. So it is generally gas defect, and this gas defect, the source of the gas, it is not just the source of the gas, might be the source of the gas, can be in the range, but the way we take the gas outside the casting matters a lot. Thank you. And another comment is, I'm having very high rough surface finish in cast iron castings. By increasing LOE, can I control the roughness? Sir, again, increasing LOE, increasing loss on ignition is, see the parameter loss on ignition, what does it tell is, when you heat this sand system, when your sand system with increased LOE is present, then you're going to say for example, loss on ignition means that means you're going to create a lot of cavities available, which is going to improve the permeability of the mold, I suppose. So how is that related to the roughness of the casting? We do not know. Maybe generally roughness of the casting is decided by the AFS number of the sand, the green, the silica sand which we use. If it is green sand or if it is any other sand system, the AFS number of the sand, and by what means you are going to increase LOI, that also matters. Maybe you're adding a coal dust or other means, or before taking that step of increasing LOI, you stratify since when you are having this problem, sir. And if you are able to highlight in these particular days you are having problem, if you're able to relate it to the already measured parameter which is available, say pouring temperature, filling time, and ingredients of the molding machine, like ingredients of the mold like coal dust, bentonite, moisture content, AFS number of the sand, whatever test you have already done, for which you already have the data, and you try to correlate with the data available, then I think you have got a clue inside the process. For every defect, the process has a clue. What we always think is, okay, let me not work for something. I'll get the idea from somebody else, and thinking that idea will work to my system, and I'll just incorporate that idea and see for the change immediately. Sometimes it does not work, sir, because the vaccine has not worked for 100% of the people who were affected by COVID. For some it worked, for some it did not work. We even have had bad experiences where people, even after getting vaccination, still lost their lives. So the solutions might look similar, but applicability of that solution to your system is to be slightly fine-tuned or tweaked. Maybe for one foundry, increasing alloy by some means can get away with the roughness, but not every time. Need for gray and castings porosity issues after machining, how to control? Sir, again, porosity issues. What is the size of porosity? Is it centerline or is it closer to the hot spot? Or since when you are getting this porosity, how is the carbon equivalent level maintained? Do you change? Do you do any change in the carbon equivalent level? Any change in the inoculation practice? Any change in, say, for example, that liquid metal temperature, filling related issues you had, and you had increased the temperature. If you are able to make a pattern or a list of all these things available, then maybe we will be able to arrive at the root cause for the porosity, sir. Because I should not tell that increase carbon, increase inoculation, add expensive inoculant, increase the size of the riser. Because all these are solutions, but these are not the right solutions. All these have to be done, might have to be done, or at least one step might be taken. I do not know. It is very difficult to solve a defect over a chat box, sir. I'll tell you frankly.
Very true, very true.
How to control slag inclusion, sir? Have you identified that whether the defect is a slag inclusion? Where is the slag inclusion? Do you have a filter in your casting? Is the slag carried away after you have removed slag using a perlator in your ladle? If you have a filter, and why is slag entering the casting? If you feel that the liquid metal outside the mold is clean and there is no slag carried away from the ladle, and there is no slag which is passing through the filter, and how is slag generating inside the casting? If the casting is generating a slag by itself while filling, then there is turbulence in the turbulence while filling. And why is there a turbulence happening? Because you would have already done a simulation ensuring proper dissolution of the proper or smooth flow of liquid metal into your cavity. When you have turbulence that is leading to a slag inclusion, then you can also look into erosion of mold happening, leading to another kind of inclusion called sand inclusion. So is it really slag inclusion? If yes, why slag inclusion? If it is slag inclusion, where has it come from? Since when you are facing this problem? So if you start stratifying in this way, sir, maybe you will be able to solve most of the defects.
Sir, I think we'll finish with one more question because it's almost
Yes.
4 or 5.
Yes, fine. Is zirconium based mold spray will help reduction in surface roughness? Sir, it might, sir, because you have any spray, any coating available on the mold surface, it is going to make it is going to reduce the severity of roughness. Might be helpful. But before doing taking an action of spraying it, you understand the root cause and then solve it at the first stage, because this is an addition of cost to your process, sir. Fine. Thank you, sir. I hope I have solved, I've not solved because solution is not possible. At least I've answered or responded to most of the queries. Thank you.
Thank you, sir. Thank you so much for your time. I saw a lot of questions asking for the presentation. For information that all the webinars from IIF will be available in the YouTube channel. So anybody who would like to address it can refer to our YouTube videos whenever you want. And back to our speaker, sir, thank you so much for a very, very well explained and knowledgeable session. With just the amount of people in our session, we can understand how people value your time and we really benefited from what we learned from you today. And I also thank all the participants who were, who attended the session and were so lovingly posted all their questions in the chat and understood that we had to be in mute so that everybody could be, have a good session and all. So, sir, I thank you again for your time and I thank you for agreeing us to, share your information and knowledge. Once again, I thank everyone for the afternoon webinar session. We'll be having many more webinar sessions every Saturday. So please stay tuned to all the messages we send through IIF. Thank you again, sir. Thank you.
Thank you. Thank you all. Thank you all for the patience. And it's weekend. Defect analysis is generally a gray area and a boring area because we don't want defects to come up. Okay, somehow we'll try solving all the defects. Thank you. Thank you all. Thanks for the opportunity.
Thank you.